Morning to one and all. Today we are discussing about open circuit and short circuit test on a single phase transformer. This is the experiment existing in electrical machines 2 lab as well as for basic electrical engineering for CSC and IT department students. So now we are discussing about the main theory is required for understanding the experiment of OC and SC test on a single phase transformer. So I will summarize some points about some transformer. Transformer is a static device, so it does not have any rotating devices. It's a energy transfer from one circuit to another circuit without change in frequency. So the main purpose of energy transfer from one circuit to another circuit is used for increase the voltage at the power generating station and used to decrease the voltage at household purposes. So main because of this energy transfer device, the transformer is used as a step up transformer or step down transformer. So in this diagram, the in this diagram, here three transformers are mentioned with red color symbol. So here at the generating station, we are increasing the voltage level for transmission of power from one place to another place. We are using step up transformer, and in between transmission lines also we are using one more transformer, and after end of the transmission line also we are using step down transformer. So here this is the one of the application for using transformer in the transmission as well as the distribution side, distribution system. So similarly, not only for this application, generally so many electronic devices or electrical devices existing some of the transformers in the very little bit size of transformers. So finally, this is about transformer. Next, coming to actually, the transformer is made up of two types of materials. Here shows first diagram representation of the transformer. This is a basic small size transformer. Now we are separating the components existing in the transformer is mentioned here. First one is iron core material. So either some steel or silicon material is used for construction of the iron core, and the another part in the transformer is copper winding. So by merging copper winding and iron core material, we got the transformer is a static device. So based on the parts existing in the transformer, based on the transformer, the core of the transformer is made of iron, whereas the winding which is wrapped over the iron core is made up of copper. So now, the corresponding parts of the transformer, there are two types of losses. Based on the there are two types of losses. First one is first part is iron core. So due to iron core, we got the iron losses in the transformer, and the other part is copper winding. So due to copper windings, the current flowing through the winding, we got the copper losses in the transformer. So by observing the transformer construction, we got two types of losses in the transformer. So the main two fundamental losses existing in the transformer is iron losses due to iron material or silicon material or aluminum material, and the other part is winding. Due to winding, current flowing through the winding, you got copper losses. So now these two iron and copper losses are measured by the open circuit test and short circuit test. So from these are the fundamental these are the fundamental losses existing in a transformer. These losses are find out by experimentally through open circuit test and short circuit test. Because open circuit test, now we go for second slide. The tests of a distribution transformer. Generally, two tests are conducted for testing of a transformer. These tests are known by different names as described below. The first one is open circuit test. The open circuit test is operated under open circuit mode. Means without applying any load on the transformer, we are conducting this test. That's why the another name for open circuit test is no load test. So this no load test, after conducting a no load test on a transformer, we got losses in the transformer is completely iron losses, because without applying any load, the transformer is not drawn more current by the windings of the transformer. That's why whatever power drawn by the transformer, the complete power is allocated for producing the iron loss in the transformer. That's why another name is iron losses test. And the another name for open circuit test is core loss test. And the second test is short circuit test. Generally the short circuit test is applied on the transformer by short circuit on one side of the winding of the transformer. So by short circuit applying on the one side of the transformer, then automatically the transformer draws full load current of the particular winding. So the under full load condition of the transformer, the transformer draws full load current of the transformer. That's why whatever current drawn by the transformer, the power drawn by the transformer is completely allotted for copper losses in the transformer. So the another name for transformer is winding losses test. So these are the other different names of the tests conducted on the transformer. Next, go through individual tests, how to observe the open circuit test and short circuit test on a transformer. So it is possible to predict the performance of the transformer at various loadings by knowing all the equivalent circuit parameters. These circuit parameters are supplied in terms of open circuit and short circuit test of a transformer. Generally, this why we are conducting two types of tests, because of without applying any loading on the transformer, we are getting these test results gives the which are used to determine the equivalent circuit parameters or performance characteristics like efficiency and regulation of the transformer. So by using these parameters, we can easily determine the efficiency and regulation of a transformer at any power factor as well as at any load condition. That is very important thing. In today we are calculating, we are the main aim of the our experimental test is predetermine the efficiency and regulation of a transformer at any power factor condition as well as at any load condition. So that is the our main aim of the our test, our experiment. And this method is of finding the parameters of a transformer is called as an indirect loading method. So why? Because in open circuit test as well as a short circuit test, we are not applying any load on we are not applying any direct load on the transformer. That's why these methods can be called as the indirect loading method. And this article enumerates how to perform these tests, how to determine the equivalent circuit parameters from the test data, and significance of high voltage side and low voltage side in which calculation to be performed. So now, after performing OC test and SC test on a transformer, we can easily predetermine the efficiency, regulation, and as well as equivalent circuit parameters from these experimental results. Now you go for individual tests, how to perform open circuit test and short circuit test on a single phase transformer. So very important points. Now I will discuss of individual tests conducting on a transformer. First, open circuit test. This test is mainly used for calculation of iron losses or core losses of a transformer. Because under open circuit test, the transformer drawn whatever power drawn by the transformer, that power is completely useful for creating the iron loss or core losses of a transformer. That's why under open circuit test, whatever power drawn by the transformer is mentioned as a core losses or iron loss of a transformer. And this test is conducted on LV side of the transformer, and HV side of the transformer is maintained open circuit. Because generally the core losses or iron losses is completely controlled by the voltage of the transformer. That's why we are conducting OC test on which side. Generally, the iron losses are constant losses, are the iron losses or core losses are constant irrespective of the rating of the winding. So generally that's why we are conducting open circuit test and LV side of the transformer compared to HV side, because the voltage rate, the voltmeter readings, and the ammeter wattmeter readings, the voltmeter, ammeter, and wattmeter ratings is very less required for LV side of the transformer compared to HV side. That's why this test is conducted on LV side of the transformer. And the main condition for conducting open circuit test is at rated voltage. So this test, open circuit test, is conducted on the transformer at rated voltage, because under open circuit test we got the iron losses or constant losses of the transformer. These losses are depends on voltage rating of the transformer. That's why this test is conducted at rated voltage. And then the last point is, under open circuit test we are using LPF wattmeter. So generally under open circuit test, the transformer is not applying any load on the transformer. That's why the transformer is not operated under no load condition. That's why under no load condition the power factor is very low. That's why we are using LPF, low power factor wattmeter, is used in the open circuit test of a transformer. And coming to next test, short circuit test. This test is mainly used for calculation for copper losses or winding loss of a transformer. So because of this test on short circuit test means, this test is conducted on this test is conducted on HV side of the transformer, and LV side of the transformer is maintained short circuit. So because under short circuit test means, one side of the winding is performing your test conducted on transformer, and another side of the winding of the transformer is maintained either short circuit or open circuit. So under short circuit, the current drawn by the transformer is full load current. That's why under full load condition, means under full load condition or under full load current drawn by the transformer, the whatever losses due to current flowing through the winding, that losses depends on the current drawn by the transformer. That's why under short circuit condition or under fully load condition, the current drawn by the transformer is creating copper losses or winding losses in the transformer. And this test is conducted on HV side of the transformer, because this main condition for conducting short circuit test is rated current. Why? Because the copper losses or winding losses are depends on the current drawn by the transformer. That's why we are conducting short circuit test is at rated current. So after applying rated current on the transformer, the current drawn by the transformer creates the copper losses or winding loss in the transformer. And under short circuit condition we are using UPF wattmeter, because under short circuit means, the completely whatever the full load rating of the transformer, that is applied on the winding of the transformer. So under full load condition, the current drawn by the transformer is full load current. So the now transformer is operating under full load current. So under full load current, the load on the transformer is full load. So the power factor operated on the transformer is approximately unity. That's why we are prepared unity power factor wattmeter is prepared for short circuit test. These are the main important points for implementing the tests on the transformer. And coming to experimental experiment, the main aim of the open circuit test and short circuit test is to determine the efficiency of a transformer. So along with efficiency, we can determine the regulation as well as equivalent circuit parameters of a transformer. Okay, next, the coming to apparatus required for transformer is, the first one is voltmeter. So here the type of the meter is mentioned MI. MI means moving iron voltmeter, because we are operating transformer under AC supply. That's why moving iron voltmeter is preferred for measuring the AC quantities. And the range of the voltmeter is 0 to 300 volts. Here two meters mentioned. The first meter is 0 to 300 volts for open circuit test, and 0 to 150 volts for short circuit test. And coming to second meter, ammeter. This is also MI type ammeter, and the range of ammeter is mentioned here two types. types. One is 0 to 2 amps per open circuit test and 0 to 20 amps per short circuit test. Because under no load test, the current drawn by the transformer is 2 to 5% of the full load current. The and we are using generally in the apparatus column we are using 2 kVA transformer. So the for 2 kVA transformer the full load current is 8.7 amps. So in the 8.7 amps, 2 to 5% means approximately 0.5 to 1 ampere. That's why we have preferred for accuracy purpose. We have preferred 0 to 2 amps MA type ammeter for open circuit test. And similarly, short circuit test. The short circuit test is operating on full load condition. That's why the full load current of the transformer is 8.7 amps. So for accuracy purpose, we have preferred 0 to 20 amps. MA type ammeter is preferred for short circuit test of a transformer. And coming to one more meter, watt meter, dynamometer type watt meter. Here also two types of watt meters are preferred for this test. The first one is 0 to 150 volts LPF watt meter. So because under no load test, we have preferred the power factor of the transformer is very low. That's why LPF 0 to 150 volts and 0 to 2.5 amps LPF watt meter is preferred for open circuit test. And the next watt meter is UPF watt meter, because the short circuit test is operated under full load condition. That's why the power factor is approximately unity. That's why 0 to 150 volts and 0 to 10 amps UPF watt meter is preferred for short circuit test. And the main component for conducting the this test is single phase transformer. Rating is to the 2 kVA transformer, and the tapping points of the 2 kVA transformer is 0 to 230 volts and 0 to 115 volts. So this is the rating of the single phase transformer is prepared for conducting the OC and SC test on a transformer. And the last one is connecting wires for conducting the experiment. And coming to circuit diagram. So first open circuit test. So the open circuit diagram is shown in the on the screen. In this is a particular circuit diagram, and this is the main transformer. The transformer rating is 115 by 220 volts single phase 2 kVA transformer. Here mentioned 115 by 220. 115 by 220 means 115 side 0 to 115 volts, that is considered as a LV winding, and 0 to 220 volts side is considered as a high voltage winding. And it means each and every transformer consists of two windings. One winding is considered as a LV winding and another winding is considered as a HV winding. LV and HV means low voltage winding and high voltage winding. And this is the this is the transformer you are conducting experiment on this transformer. And clearly observing the transformer, the components and power supply is connected on the LV side, and HV side is maintained open circuit, because open circuit test is conducted on LV side of the transformer. Because the under open circuit test, we are getting the power, the losses generated by the transformer is constant losses or iron losses or core losses of a transformer. These losses are depends on the voltage rate drawn by the transformer. That's why we are conducting this open circuit test under rated voltage. So that's why this test is conducted on either side of the transformer. But LV side you are preferred means for we are conducting open circuit test on LV side, then the ratings of the meters required for measuring the values is very low compared to HV side. That's why we are preferred conducting open circuit test on LV side only. And the coming to meters connected to the transformer is and one more device. This is the watt meter, consists of four terminals: main, line, and C and V. M means main, C and means common, L means line, and V means voltage. So these are the four terminals of the wattmeter. Is every wattmeter consists of four terminals, and the rating of the wattmeter is 0 to 150 volts, 2.5 amps LPF wattmeter. So, and the ammeter 0 to 2 amps and voltmeter 0 to 115 volts. And here one more device is used for getting the variable AC supply, because at the main supply we are getting constant fixed voltage, that is means 0 to 230 volts 50 single phase AC supply we are getting from the main power supply. So that is applied to the transformer through auto transformer, because directly we are not applying sudden voltage on the transformer, because in case sudden voltage you are applying, then automatically the meters or whatever devices connected to the power supply, some devices will be malfunctioning or damaged due to the sudden spike of voltage applied to the devices. That's why slowly how much voltage required for operating the open circuit test and transformer. Slowly we are varying from zero voltage to maximum voltage by auto transformer, single phase auto transformer 230 volts by 20 to 270 volts rating. And these are the components required for conducting the open circuit test. Now I am explaining how to connect the circuit diagram as per our requirement. So first we take connections from main power supply, and that is connected to auto transformer, and the other side of the auto transformer is connected to voltmeter, and the voltmeter is connected in parallel with the power supply because the voltmeter voltage is maintained constant in parallel. That's why voltmeter is connected in parallel with the auto transformer, and the ammeter is connected in series with the power supply because the current is maintained constant in series components. That's why ammeter is connected in series with the power supply, and the current coil of the M and L, in between M and L consists of current coil, and C in between C and B consists of voltage coil. And the current coil of the wattmeter is connected in series with the power supply, and the voltage coil of the wattmeter is connected in parallel with the power supply, and the LV side is connected to the power supply, and HV side is maintained open circuit. Now the connections part of the transformer is over. Now step by step procedure how to conduct the open circuit test on a transformer. So connections are made as per circuit diagram. Ensure the variac is set to zero output position before starting the experiment. And before starting the experiment, you have to take some precautions of the each and every component. You have to maintain the knob or variac is at zero position, and all meters are maintained 0.0 point zero one. The pointer shows zero reading or not. After that, switch on the power supply. Now apply the rated voltage on primary side of the transformer by using variac. So what how much voltage how much rated voltage is maintained on LV side of the transformer? This is the LV side transformer, rated voltage is 115 volts. So now the pointer here, the auto transformer pointer is at minimum position. Now the pointer is may varying from minimum position to maximum position, and observe the rated voltage across the voltmeter. After getting rated voltage, how much voltage? 115 volts is the rated voltage of the transformer. After getting 115 volts, note down the voltmeter, ammeter, and wattmeter readings. The readings of the voltmeter, ammeter, wattmeter readings are noted in the tabular column, and then variac is set to zero output position and switch off the power supply. After getting the readings across the voltmeter, ammeter, and wattmeter, and minimum and set to variac knob position to zero output position, and switch off the power supply, and perform the performance of the transformer with help of the formulas given. Okay, so here this is the tabular column you are observed in the open circuit test. The voltmeter reading I mentioned V naught is the no load voltmeter reading, and the ammeter I naught reading is mentioned under no load test. The ammeter drawn by the transformer is I naught, and the LPF wattmeter reading mentioned W naught. So now under open circuit test we got V naught, I naught, W naught. So these are the single reading experiment. Under single reading experiment, the wattmeter reading W naught shows whatever power drawn by the transformer is mentioned by the wattmeter reading. Under no load test, the wattmeter reading shows whatever reading that show reading is represented for constant losses or iron losses or core losses of a particular transformer. Now we got one of the losses finding from the open circuit test. Now go to second test is short circuit test. This test is also performed similar to the open circuit test, but the main difference is here this test, short circuit test, is conducted on a high voltage side. This test is conducted on high voltage side, and LV side is gets short circuited. that is shown clearly in the circuit diagram. Here this is the main circuit transformer, and the one here some mistake, 220 by 115 volts single phase 2 kVA transformer. Here HV side is 20 to 230 volts and LV side is 0 to 115 volts. So the short circuit test is conducted on high voltage side of the transformer, and low voltage side of the transformer is gets short circuited. So that is clearly shown in here. And the voltmeter, ammeter, wattmeter is also connected to the high voltage side of the transformer is similar to open circuit test. And the other component is a single phase auto transformer 230 by 270 volts single phase auto transformer. And the power supply is connected to the auto transformer 230 volts phase single phase auto transformer, single phase AC supply. And here major difference is here 0 to 150 volts voltmeter is sufficient, because here under a short circuit test the test is conducted at rated current. The rated current of the transformer is finding by the rating of the transformer by the high voltage of the transformer, means 2 kVA by 230 volts, means we got 8.7 amps. And it means we are operating short circuit test on a transformer at rate 8.7 amps, means up to 8.7 amps we are applying on the auto transformer. Then we got the voltage of the voltage drawn by the transformer at rated current is 5 to 10% of the rated voltage, means 23 volts, means maximum 23 volts drawn by the transformer at rated current. That's why we will prefer the low voltage, low rating voltmeter is preferred for short circuit test. And the current the ammeter used for a short circuit test is 0 to 20 amps moving iron ammeter. And the wattmeter is UPF wattmeter, because under short circuit test the load on the transformer is applied full load. Under full load condition the power plate operated on the transformer is approximately unity. That's why you are preferred 75 by 10 amps UPF wattmeter. And similar to the open circuit test, here also wattmeter used in short circuit test is also similar type. The wattmeter consists of four terminals, main, line, and current and voltmeter. So this is the connections point of view. The same the whatever connections you are connected in the open circuit test, the same connections applied to the short circuit test also. But the major difference is short circuit test is connected on HV side and LV side is short circuited, and the rating of the meters also modified. And now step by step, now we'll see the step by step procedure how to conduct short circuit test. Connections are made as per circuit diagram. Ensure that the variac is set to zero output position before starting the experiment, and observe the pointers shown by the meters. All are pointers are shown zero reading or not. And now switch on the power supply and apply the rated current of the primary winding of the transformer by using variac. Now we got the readings of the voltmeter and ammeter. Wattmeters are noted down in the tabular column. And then the variac set to zero output position and switch off the power supply. And now now we calculate the performance of the transformer and the efficiency of the transformer by using formulas given below. And the observations of the short circuit test is noted in the tabular column. The voltmeter in the short circuit test, the voltmeter reading shows VSC, and ammeter reading shows ISC, and wattmeter reading shows WSC. Here the wattmeter reading in the short circuit test, the wattmeter reading shows completely the power drawn by the transformer, and the short circuit test is useful for creating the copper losses or copper losses of the transformer. That's why in the on the short circuit test, the wattmeter reading shows reading is considered as a full load copper loss of the transformer, because we are operating short circuit test under full load condition. That's why the wattmeter reading shows full load copper loss of a transformer. Now we are completing the demo required for completing conducting the open circuit test and short circuit test on the transformer. Now we'll go for a practical experimental view of the OC and SC test of a transformer.
So today our lab, electrical and electronics engineering lab, today we are discussing about open circuit test and short circuit test of a single phase transformer. So in this experiment, this is the open circuit test circuit diagram. So in this experiment we are using single phase transformer. So the nameplate details of the single phase transformer is shown here. Single phase transformer KVA rating is 2 kVA and primary voltage is 230 volts, secondary voltage is 115 volts, and the rated current is 8.7 amps make by ITL make. So this is the, now we are seeing what are the components we are using in this experiment. The first main component is 2 kVA single phase transformer. So this is the single phase 2 kVA transformer. In this transformer, the main common terminals is here shown 0 to 230 volts and another terminals is 0 to 115 volts. So this is the 2 kVA single phase transformer. The main terminals of this transformer is 0 to 230 volts and another one is 0 to 115 volts. We can utilize the terminals as per our requirement. In case we want to use this transformer as a step down transformer, then 0 to 230 volts we can utilize it as a input terminals and 0 to 115 volts act as a output terminals of the transformer. So as like step down, this transformer you can utilize it as a step up transformer. So in that case step up transformer 0 to 115 terminals acting as a input terminals and 0 to 230 volts terminals acting as a output terminals of the transformer. So this is the main terminals of the 2 kVA transformer. So this is the main component of our experiment. And next coming to second component is single phase auto transformer. So this is single phase auto transformer. The rating of the single phase auto transformer is here shown. The input is 0 to 230 volts. Here 0 to 230 volts you are applying from the main power supply and the output we are getting in between 0 to 270 volts. So this is 0 to 270 volts that is variable output voltage you are getting from this auto transformer. So this is the main device for applying variable AC supply for the experimental purpose. So this is the here shown from the rating of the output voltage you are getting by varying this knob. So from it shows 0 to 20, 40, 60, 80 like that up to 270 volts it shows. Okay, as per our requirement we are modifying this knob as per output voltage requirement. And coming to components. So for our experiment, the main components required for our experiment is voltmeter, ammeter and wattmeter. So in this open circuit test, we are applying the voltage level for the open circuit test is 0 to 115 volts, because here the transformer side is 0 to 115 volts. We are connecting open circuit test. So for this voltage measurement, we are connecting voltmeter range is 0 to 150 volts. So this is the voltmeter we are using for open circuit test. The scale of the this voltmeter is 0 to 150 volts. So this scale is enough for open circuit test. We want to increase the voltage level, then we are using second scale 0 to 300 scale we are using. So and the connecting points is common terminal and 150 and 300. So in our experiment open circuit test we are using 115 volts voltage level. So 0 to 150 is the common terminal and 150 terminal is sufficient for open circuit test. So these two terminals are using for connecting the voltmeter in our experiment. And coming to ammeter, in the open circuit test the range of the current drawn by the transformer is nearly 2 to 5% of the full load current. So in our experiment here 2 kVA transformer, in this 2 kVA transformer you are connecting 115 volt side. So generally 115 volt side you are conducting experiment on transformer under open circuit, under secondary open circuit. Under open circuit condition the transformer drawn only 2 to 5% of the full load current. So that 2 to 5% means we are considering 5% of the full load current means that is less than 1 ampere. So that's why the ammeter range is we are using 0 to 2 amperes. So because up to 1 ampere the transformer is drawn, so for convenience purpose we are taking 0 to 2 amperes current source ammeter. So this is the ammeter for measurement of current in the open circuit test. Next component is Next component is wattmeter. So this is the wattmeter. This is the wattmeter we are using for open circuit test. This is low power factor wattmeter. So how it is identifying that here shown cos pi is equal to 0.2. So this cos pi 0.2 means low power factor indication. So why are you preferring low power factor meter is discussed in the theoretical concept. And coming to connections of the wattmeter, the main component, the main terminals of the wattmeter is line, main and common and voltage. So L, M, C and V. The V is chosen here based on the applied voltage. So here we are utilizing 115 volts in the open circuit test. So 150 volts terminal is sufficient for connection of V terminal. And another terminals is the range of the wattmeter is identified by the connection of these terminals. So here B1 and B2 is connected, short circuited. So B1, B2 means based on these two terminals, we are identifying the range of the voltmeter from these named details. So here B1 and B2. Here B1 and B2 both are short circuited. For particular B1, B2 short circuit, the current range of the wattmeter is 2.5 amps. So for this particular 2.5 amps, we are connecting 150 volts side. So current rating is 2.5 and 150 corresponding multiplication factor is 0.5. So as per namely details, we are considering multiplication factor for this wattmeter. Okay. So now we are completing the individual components used in the open circuit test. Now we will go for next step is connections, how to connect the connections with apparatus for smoothly conducting the experiment. Now we will see the connections of the open circuit test and single phase transformer. So as per the circuit diagram, we are connecting one by one each and every component as per the circuit diagram. So in this one, this is the auto transformer. This is considered as auto transformer. This device gets power supply from this terminal, and this auto transformer is connected to voltmeter. So this is auto transformer first terminal, and this is connected to voltmeter. Here voltmeter 150 volts terminal is connected to auto transformer. Okay, and this continuation voltmeter other next component is ammeter. So the other term, this continuation voltmeter continuation is connected to ammeter. This is ammeter primary terminal is connected to this is the ammeter, and next continuation from ammeter to wattmeter. So this ammeter is another terminal. The ammeter is connected in series with the power supply. So that's why the input is connected to here and output you are taking from this another terminal. Okay. So ammeter is connected in series with the power supply. This continuation as per circuit diagram, ammeter other end is connected to main power supply. So the wattmeter M terminal is here. So this is connected to ammeter. And M here in the wattmeter M and C both are short circuited. So M and C both are short circuited. Okay, next continuation from the L terminal. From this continuation, L terminal is here. So the L terminal the L terminal continuation is connected to main transformer, single phase transformer. So in this process, we are identifying. So generally, open circuit test is conducting on LV side. So we are identifying difference between these two terminals. So this is high voltage side and this is LV side. So the L continuation is connected to 115 volt side. So why are you connecting on LV side is discussed already in the theory part. So LV side is connected, wattmeter continuation is connected to LV side of the single phase transformer, and this continuation zero terminal is connected to main power supply. So the last terminal of the wattmeter is V terminal. So the V terminal here chosen according to applied voltage. Here 150 volts and 300 volts, both terminals available. So we are using 150 volts because we are operating this experiment on 115 volts. That's why we are choosing 150 volts terminal for convenient purpose. V terminal is considered as a 150 volts terminal. This is 150 volts is connected to auto transformer input terminal, input side. So Now all connections are completed. Now we are conducting experiment. So first, before starting experiment, first of all we are observing the point, the meters parallax error. All meters are shown 0.0 reading, 0 position. So without parallax error we start the experiment, and before starting experiment we observe the knob of the auto transformer is maintained 0 position or not. So this is at 0 position. So now we will ready to start the experiment. Now switch on the power supply. So here the switch on the power supply. Now we got the power. Now you got the power across the auto transformer. Now the main condition for operating the open circuit test is we are operating the open circuit test at rated voltage. So what is the rated voltage of the transformer? The rated voltage of the transformer is 115 volts. So this is the 115 volts we are conducting the experiment of single phase transformer. So the rated voltage is 115 volts. So by varying the knob of the auto transformer, up to this knob will be varying up to we are getting 115 volts across the voltmeter reading. So we slowly increase the voltage applied of the single phase transformer. The voltage applied to the transformer will be increased from 0 to 50, 60, 70, 80, like that up to 115 volts. Up to 115 volts we are increasing the knob of the auto transformer. So now we got 115 volts. So now 115. Okay, now we got 115 volts. So now note down the readings of the voltmeter. Now note down the readings of the voltmeter. Voltmeter reading is 115 volts and current is approximately 0.049. And why you are getting low voltage, low current? Because we are operating under no load condition. The current drawn by the transformer is 2 to 5% of the full load current. So we got approximately 0.5 amps, and the wattmeter reading is exactly 40 watts. But we are not note down directly 40 watts because this multimeter has some multiplication factor. So actually, according to our connections, the multiplication factor of the wattmeter is 0.5. So 40 into 0.5 means 20 watts. So this is the readings of the single phase transformer under open circuit test. So only 3 readings: voltage 115 volts and current 0.5 amps, and wattmeter reading is 20 watts. So this is the single reading. After getting all these readings and minimize the auto transformer from maximum position to minimum position slowly up to 0 voltage. The voltage shows 0 voltage. Up to 0 voltage we minimize the auto transformer. After getting 0 voltage across the auto transformer, switch off the power supply. Okay, next continuation, the next in the OC and SC test of a single phase transformer, the next test is short circuit test on a single phase transformer. Already why you are conducting this test on a transformer is already discussed in the theory part. How to conduct this experiment? This experiment is also conducting in similar manner of the open circuit test, but the main difference is of this test is in the previous experiment we are conducting open circuit test on LV side, but short circuit test is conducting on HV side, and LV side is short circuited. So that is the main difference in the short circuit test and single phase transformer. So in this is the main transformer. In previous experiment we are conducting experiment on LV side. Now short circuit test is conducting on HV side. So 0 to 230 volts you are choosing for conducting the short circuit test on a single phase transformer. This is the we are connecting terminals, and this is the short circuited terminals. Okay, so and another point is the meters also changed for the short circuit test, because in the short circuit test the voltmeter range is very low, the 5 to 10% of the full load voltage. So up to 23 volts you are getting. So 0 to 75 volts you are taking voltmeter range. And ammeter is also we are considering 0 to 10 amperes, because the rated current of the single phase transformer is 8.7 amps. So for that purpose 0 to 10 amperes rating we are taking for the ammeter. And here considering wattmeter is the wattmeter you are considering here, this is unity power factor wattmeter. So why means we are operating transformer on full load condition. So that's why you are connecting UPF wattmeter. So this is the main difference between short circuit test and open circuit test. Now we will go for connections of the components to the transformer. So as per previous experiment, we are connecting all these components. First we are considering the output terminal of the auto transformer. The output terminal of the auto transformer is connected to voltmeter. Here we are considering voltmeter range here 0 to 25, 50, 75. So we are considering the 0 to 75 you are taking. The scale is also shown here 0 to 75. So whatever reading shown by the voltmeter, directly we are measured in between 0 to 75. So directly I am taking 0 to 75 range of this voltmeter, and the voltmeter continuation is connected to ammeter. We start the connections from the auto transformer. The auto transformer output terminal is connected to voltmeter, and the voltmeter output terminal is connected to ammeter. Here ammeter input terminal is here connected to ammeter, and ammeter continuation is connected to here taking 0 to 10 amperes. So here ammeter ranging shows 0, 20, 10. So here 0 to 10 I take the range of the ammeter, and the 10 amperes is connected to wattmeter main terminal. Here main terminal, this is the main terminal, and main and common is short circuited. MC shorted, and L is connected to, so L is connected to transformer, single phase transformer on 230 side. Here 230 side, the transformer is 230 side, you are connecting wattmeter, because SC test is conducting on high voltage side. That's why you are prepared 0 to 230 volts connected to wattmeter, and continuation transformer other end is connected to transformer other end is connected to here another wire. ఇక్కడ నుంచి ఒక వైర్ వస్తుంది కదా V. Now wattmeter V terminal, V is here taken 75. So here wattmeter V terminal is connected to 75 range, that is connected to auto transformer through voltmeter. The voltmeter other terminal is connected to auto transformer. Now and the another main important connection is in previous experiment, one side you are connecting, other side is kept at open circuit, but in this experiment one side means high voltage side you are conducting experiment, and LV side we have to short circuit the LV side. So the LV side means 0 to 115 volts, this can be short circuited. So now the main transformer secondary winding is short circuited. Okay, so now connections completed. So the main thing in the experiment is the main transformer, the SC test is conducting on 0 to 230 side, and 0 to 115 side is short circuited. That is the main important connections in the short circuit test. The remaining connections are similar to the open circuit test. Now switch on the power supply. All these connections are before switch on the power supply. Observe the pointers of the all meters, but here shows the voltmeter shows deflection, some deflection. We have to modify. Here voltmeter deflected from the 0 position, so we have to maintain the pointer at 0 position. So that is without seeing these errors, we start the experiment, we got some measurement errors in the voltmeter. So we have to mention the pointer at 0 position. Now voltmeter shows 0 reading, and ammeter shows 0 reading, and wattmeter shows 0 reading, and the auto transformer is also maintained 0 position. Now switch on the power supply. Now switch on the power supply. Now we got the power across the auto transformer. So after getting power across the auto transformer, the knob of the auto transformer is varying from 0 position to slowly increase the voltage across the transformer. So this knob will be varying up to the main condition for the main condition for operating the short circuit test on a transformer is rated current. The rated current of the transformer, the rated current is 8.7 amps. The rated current of the transformer is 8.7 amps, and means whenever you are operating the knob of the auto transformer, Slowly observe the ammeter reading also. Parallelly you are observing the ammeter reading. The ammeter reading shows 8.7. Up to the knob will be varying up to ammeter reading shows 8.7 amps. So now the ammeter reading is gets 8.7 amps. Now we got the ammeter reading approximately 8.7 amps. Now note down the voltmeter reading. The voltmeter reading shows 15 volts. The voltmeter reading shows 15 volts and ammeter reading shows 8.7 amps and wattmeter reading shows 110 volts, 110 watts. So this is the single reading experiment. In this process, after getting the readings of the voltmeter, ammeter and wattmeter reading, after that, after note down all these readings, you have to minimize the auto transformer from maximum position to minimum position of the current drawn by the transformer up to 0 amps. So after minimize the auto transformer to minimum position, switch off the power supply. So now we are completing the short circuit test on a transformer based on the readings getting from the open circuit test and short circuit test. The next calculation part will be discussed in the next section. Thank you.
Now, up to now, we are completing the practical experimental procedure on OC and SC test and single wave transformer. Now, after getting the experimental readings, so how to calculate the efficiency of a particular transformer. So now we'll see the step-by-step procedure of calculations for finding the efficiency of a transformer. So in this process, the first tabular column mentioned here observations from OC test. So from the OC test, we are getting no load voltage V naught and no load current I naught and wattmeter reading W naught. So this particular readings, but this particular tabular column, the wattmeter reading W naught under open circuit test is mentioned. W naught reading is completely iron losses of the particular winding or constant loss of the winding of the transformer. And the second tabular column observations from short circuit test. From the short circuit test, we are getting the similar type of readings, that is VSC and ISC and WSC. Voltmeter reading is VSC, ammeter reading is ISC, and wattmeter reading is WSC. In this from this tabular column, the wattmeter reading WSC reading is mentioned about the full load copper losses of a particular transformer, the full load copper loss of a particular transformer. So from these readings, step by step, we are calculating all these parameters. From the no load test conducted on the LV side of the transformer. So from the open circuit test, we are getting W naught, V naught and I naught. So from the W naught, the no load input power applied to the transformer W naught is equal to V naught, I naught plus phi naught. From this formula, we know already W naught, V naught and I naught. So the unknown parameter is cos phi naught. That is cos phi naught is means no load power factor. That is cos phi naught is equal to W naught by V naught I naught. So from this tabular column, we are getting no load power factor of the transformer, that is cos phi naught. And the next component is magnetizing component reactance of the transformer, that is V naught by Im. And next magnet working component of the transformer, that is IW is equal to I naught cos phi naught. That is W naught by V naught. W naught by V naught. So next the magnetizing component of current Im is equal to I naught sin phi naught. So after getting no load power factor, directly by multiplying no load power factor with I naught, then you get working component of the current. And from the no load power factor, the cos phi naught, we are calculating sin phi naught by using mathematical equation. After that, I naught sin phi naught is represents the magnetizing component of current. So finally, we got core loss resistance Re is equal to V naught by IW, that is working component of current, and magnetizing component of reactance Xm is equal to V naught by Im. So these two parameters are useful for constructing the equivalent circuit of a particular transformer. And next from the short circuit test, the short circuit input power WSC is equal to ISC square RH, and equivalent resistance RH is equal to WSC by ISC square. Already we know about WSC and ISC. From the short circuit test tabular column, we got WSC and ISC and VSC. By using these three parameters, we are calculating equivalent resistance and HV side is equal to RH is equal to WSC by AC square. And equivalent impedance on HV side is equal to ZH is equal to VSC by AC. After getting RH and ZH from the equivalent impedance formula, we got equivalent reactance HV side SX is equal to square root of ZH square minus RH square. So from this calculations, we got all equivalent circuit parameters of a particular single phase transformer. So now we are seeing the how to find the efficiency of a particular transformer. So from suppose we want to calculate a particular, the efficiency of a transformer at particular load, means the load on the actually we are conducting experiment on full load condition, but we want to calculate the efficiency of a particular transformer at the desired load. That load is assumed as a off load or one fourth load or three by fourth load or full load, like that we are assuming as a load condition on the transformer. Suppose I am taking example at off full load of a particular transformer. The copper losses is calculated at a off load is assumed as a WS into 1 by 2 whole square. Because why? Because they actually the copper losses is depends on the copper losses completely depends on current rating of the transformer. So whenever you are increasing load on the transformer, definitely the current drawn by the transformer is also increases. So the automatically the copper losses also varying with respect to load on the transformer. So it depends on every particular load. The copper losses is also varying with respect to load on the transformer. So that's why the copper losses at a desired load is calculated by WSC into half whole square into 1 by WSC into x square watts. XC is here, XC means 1 by 2, where WSC is the full load copper losses. And the constant losses is from, we are getting from the no load test on a transformer. So no open circuit test or no load test on a transformer. That is W naught. We are getting W naught from the open circuit test on the transformer. And the WSC we are getting from the short circuit test on a transformer. Finally, we are calculating output power of the transformer is X kVA into cos pi. That is the formula for calculating the output power of the transformer. X means load on the transformer, and S means kVA rating of the transformer, and cos pi means power factor of the transformer. So by using these three parameters, we are calculating output power of the transformer. Here output power is mentioned of kVA transformer. Off means load on the transformer, and kVA means kVA rating of transformer. Cos pi means the power factor of the transformer. Finally, we got input power of the transformer is represented by the output power plus copper losses plus constant losses. Finally, we got input power. After getting input power and output power, you can easily calculate the efficiency of a particular transformer. Means output power by input power into 100. So this is the procedure of calculating the efficiency of a particular transformer. So this is the one small calculation how to calculate the efficiency of a particular transformer from the tabular column readings. So in this tabular column, open circuit test readings is V naught, I naught, W naught, and short circuit test readings is VSC, ISC, WSC. So this is the tabular column readings. From this tabular column, from the open circuit test, W naught reading mentioned 23 watts. That is constant loss of the single phase transformer. Whatever wattmeter reading mentioned in the open circuit test, that is completely that particular power watts mentioned about complete constant loss of the single phase transformer. And from the short circuit test, whatever wattmeter reading mentioned WSC, the WSC meter reading shows complete copper losses at full load condition of the transformer. That is 120 watts is mentioned full load copper loss of the transformer. So now after that, KVA rating of transformer is we are conducting transformer this particular open circuit test and short circuit test on 2 kVA transformer. So the KVA rating of transformer S is taken as a 2 kVA, and the power factor I am assuming as a power factor on the transformer is zero point 0.8, and the fraction of load on the transformer is assumed as a off load. So now output power of the transformer is XSK cos pi. X means the fraction of load on transformer is of 1 by 2, and S is kVA rating is 2 kVA and power factor is 0.8. So then automatically after substituting x, s and cos pi, we got output power of the transformer. And the total losses in transformer is calculated by W naught plus x square WSC. Because x square, why are you multiplying x square with WSC? Generally, the WSC means full load copper loss of a transformer. These copper losses depends on the current drawn by the transformer. That's why depends on the load on the transformer. The copper loss is also varying. That's why we are multiplying x square with WSC. Okay, so after getting total loss in the transformer, we are substituting W naught and WSC in the total loss in the equation, total loss in the transformer equation. So, in the total input power of transformer is output power plus total losses. So, input power is equal to X, output power means Xs cos by plus total losses means W naught plus X square WSC. So, now is substituting these formulas in the efficiency of the transformer. Efficiency of a transformer eta at x load is equal to output power by input power into 100. So efficiency at x load is equal to s x cos pi by x s cos pi plus w naught plus x square WSC into 100. Now one by one you are substituting all these values in this particular formula. X is equal to offload. I am assuming as the load on the transformer is offload. So X is equal to 1 by 2 at a particular offload. X is equal to 1 by 2 into kVA rating 2 kVA into power factor of the load is zero point 0.8 by X 1 by 2 into 2 kVA into zero point 0.8 plus no load no load the iron losses is equal to 23 watts plus X square 1 by 2 whole square into copper losses at full load is 120. So after substituting all these values in this particular formula, so finally we got the efficiency at offload is equal to 93.78%. So in this manner, we have to calculate the efficiency at a required load and at required power factor. This is the procedure of calculation for efficiency of transformer at desired load and at desired power factor. So in this similar manner, we are calculating all these parameters at required condition. So this is the tabular column mentioned fraction of load on the transformer is mentioned 1 by 4, 1 by 2, 1 by 4 and 1. Similar way, power factor at all conditions is considered as a zero point 0.8 and the output power is excess cos pi. So X means fraction of load and S means kVA rating and power factor is assumed zero point 0.8. So we are calculating output power and the total losses is PI means constant losses plus X square into copper losses. So after getting total losses by adding output power and total losses we got input power. So finally we got efficiency is equal to output power by input power is equal to efficiency of the transformer. After getting the efficiency at different loads, we draw the after a similar manner whatever calculations we have did at particular power factor zero point 0.8. Similar way, we have to calculate all these values for different power factors like 0 0.8, 0 0.7, 0 0.6, 0.5, 1. Like that, we have to calculate all these values for different power factors and different loads on the transformer. After getting the efficiency at a particular power factor and particular load, the graph can be drawn between percentage of efficiency versus output power in kilowatt. So the model graph is shown here. The graph is drawn between percentage efficiency versus output power in kilowatts. Means the last column versus the output power. The last column efficiency versus this column output power. So we drawn between the curve between efficiency versus output power. The curve is coming like that. So here in this graph the curve is drawn for two different power factors, that is cos pi 1 and cos pi 2. So the curve is coming similar way for both power factors, but the variation between these two curves is the percentage of efficiency will be modified with respect to power factor. The power factor will be increased, then automatically the efficiency of the transformer is also increased. So that is conclusion from this graph. So finally, this is the calculation part is completed. Thank you.